Hi everyone, my name is Pradyumn Kejriwal and today we'll discuss the solution to the sixth problem from the CP sheet by TLE Eliminators in the rating of 1400. Alright, so let's begin. I'll open my CP sheet to find the problem, and as you can see here, I have a link to my problem, so I'll click it. Alright, so the problem is called Iva and Pav. Iva gave Pav an array A of n elements. Let us define FLR as AL and AL plus 1 and up to AR, where AND is the bitwise AND operation. Note that FLR is not defined when L is greater than R. Eva also gave Pav Q queries. Each query consists of two numbers K and L, and she wants Pav to find the largest index R such that f of L, R is greater than or equal to K. Pav wants to solve this problem fast because he doesn't want to upset Eva. He needs your help. Okay, so what you have here is a problem which says that we have an array. All right, we have an array A of length n. So let's say it is A1, A2, A3 up to AN. All right, and we are given Q queries. We are given Q queries of the form L, K, where L, K means that we have to find out. We have to find out the largest R such that f of L, R is at least K, so greater than or equal to K, where f of L, R is defined as the range and of the indices L to R, so, or basically AL plus 1 and up to AR. So the range and of AL plus 1 up to AR, right? So this is the bitwise AND operation, bit of AL to AR, right? So you have to find for each query the highest R such that this function is greater than or equal to K, right? So now let's look at sample sum. Like for example, we have this sample right here, 75317. Okay, so we have 7, 5, 3, 1 and 7, and the queries, let's say the first query we have 1, 7. So that means L equal to 1. So my L is right here and my K is equal to 7. So what I want is that I want to choose the maximum R such that the range and from L to R should be at least 7. So let's say I choose this R. Okay, then this 7 and 5. 7 and 5 becomes 5. So which is less than or equal to 7. So 7 and 5 becomes 5, which is less than or equal to 7, which is our K. So therefore I cannot take this R. I cannot take this R. And similarly you can verify for this R also. Like 7 and 5 and 3. 7 and 5 and 3 becomes equal to 1, which is less than or equal to 7 still. So we cannot take this R as well. And similarly you can prove that we cannot take this R, and also we cannot take this R. But what if we take this R? If we take this R, then our AND is just 7. Like in our range, there's only one number which is 7. So our function, like f of L, R is equal to 7. So we can actually take it. Like this R is valid. So the highest R which is valid is 1. Like all of those above, all of the R's which are greater than 1 are not valid. So our answer is just 1 for this query, right? So the answer is 1. Now similarly you can check the answer for the other queries and also the other test cases that they have given. Also there's one more thing, that if there is no such R for which f of L, R is greater than or equal to K, then you have to print -1. Like if f of L, R is less than K for all R which is greater than or equal to L, then print -1. Okay, that's the problem. So how do you actually solve this? Before that, let's see the constraints. So we have n up to 2e5 and q up to 1e5, and like the sum of n and q are both 2e5 and 2e5. All right, and in your queries the numbers l and k are also pretty large. So L is an index obviously, so it is up to n, and k is up to 1e9, and the numbers are also up to 1e9. right? So anyways, so since n and q are up to 1e5, you cannot actually do it in O of n into q. You cannot do it in O of n into q because you are only allowed 1e8 operations per second per test, right? And since their sum is up to 2e5 in fact, so you cannot do it. All right. So you have to do something like O of n plus q or something. Okay. Or maybe some log here or there, like n log ai or n log n or something. So that is fine. But you cannot do O of n into q. All right. So you can pause the video now if you want to try the problem for yourself. Alright, so I'm assuming that you have tried the problem and now you want to see the solution. Okay, so let's begin the solution. So how do we solve this problem? Now to solve this, there is one simple observation. Okay, and how do we come to that? I'll tell you. So we have to actually use one property of AND. Like we are doing bitwise AND here, right? We are doing bitwise AND. So we have to use one property of bitwise AND. So the property is that A and B, if I have a number A and I take its AND, the bitwise AND with B, then it is definitely less than equal to A, right? So that means if I have a number and I take a bitwise AND with another number B, then it can either make the number same or it can make it less than that. So the proof is quite simple. Like let's say your A is something 10110. So whatever you take the bitwise AND, like let's say you take the AND with this number, then all of the zeros will remain 0 in your bitwise AND as well, and all of those ones, the ones might become 0 or 1, right? So either they can become 1 or they can become 0. So definitely the number can only reduce. Like if the ones become 0, then the number reduces, and if the ones, like all of the ones, stay 1 in your result, then the number stays the same. It doesn't decrease. But in no case can the number increase when I take bitwise AND with some other number. So if I do A and B, then it can be never greater than A. It can never be greater than A. Alright. So that's the property. So by looking at this, we can actually think about how FLR behaves. Like we have our function, right? We have our function f of L comma R, which is defined as AL and A of L plus 1 up to A of R, right? And in each query we have a fixed L, right? In each query we have been given a fixed L and we can change this R. We have to actually tell the maximum R. So how does it actually behave? Like how does the function behave? My claim is that this function f is monotonic. And what do I mean by that? I mean that as you increase this R, the function will keep decreasing. Okay, so like for example, how do I actually prove this? Like let's say I'll just illustrate it. So we have a1, a2, a3 up to an. So let's say your L equal to 2. Okay, your L is 2. Then let's say either R can be here, or R can be here, or R can be here, and so on. So let's say that R equal to 2. For R equal to 2, what will be the answer? So the value of FLR will be just A2, right? Then for R equal to 3, the value of FLR will be A2 and A3. Then for R equal to 4, the value of FLR will be A2 and A3 and A4. So as I told you that taking an AND with a number reduces that number. So when I take an AND with any number to A, then it is less than equal to A, right? So here I start with A2. Then since I took an AND with A3, so definitely this number is less than equal to A2, right? Then I took an AND with A4. So definitely this number is less than equal to this number, and which was less than equal to this number. So I can say that as I am increasing my r, my function is decreasing, or not decreasing, it is non-increasing. That is, it can remain the same or it can decrease. So if I make a graph, then it kind of looks like this, right? This is my function f with respect to r. Okay, and I want to find out that for certain L, like for a certain L, I want to find out that at which point does the function go less than k, right? So actually, if you can notice here, the function is monotonic, and we want to find out the maximum r for which the function is greater than equal to k. So we can use a pretty familiar idea here. Like, I'll elaborate. So let's see. Let's say you have the array of length 7, let's say a1, a2, a3, a4, a5, a6, and a7, right? And let's say your L equal to 2 again, L equals to 2. So now let's say you have a value of k. So your L is equal to 2 and you have a value of k. So when you find the different values of the function, like at r equal to 2 you find, at r equal to 3 you will find, at r equal to 4 you will find, and 5, 6, and 7, you will find that the values are decreasing, right? So at some point, like if initially, let's say initially it was greater than equal to k, okay, and okay, if it is greater than equal to k, if the value is greater than equal to k, then I am denoting it by 1, and the value, if it is less than k, then I am calling it 0. So it is possible, like let's say it starts out at 1, then when you take r equal to 3, so it will be something less than this value, so it can be 1 or 0. Then here also it can be 1 or 0. Like let's say that till this point the function is greater than equal to k. Now when I take the AND with a5 also, the function becomes less than k, so it becomes 0. Like not 0, but I'm denoting it by 0 where the function becomes less than k. Then if I take an AND with a6 also, then definitely I can say that since the function till here, like since the AND of these numbers is less than k, so I can say that the AND of these 5 numbers is also less than k. So it will be 0 0 0 all along. So this will look like that. Like initially for some r, my function will be greater than equal to k, and after a certain point it will be less than k. And it is possible that it is like this 1 1 1 1 1. So that is no problem. Like this is also possible, and it is also possible that it is just 0 0 0 0 0, right? This is also possible, but essentially what we are trying to do is find out the last one in this sequence of ones and zeros. Okay, so like the last one's index. So since here the last one occurs at 4, that means that till 4, like if L equals to 2, then till r equal to 4, my bitwise AND is at least k. So how do I find the last one? It is a very classical problem. It is solved using binary search. Okay, I can simply solve it using binary search on r, right? So what we'll simply do is that we have the certain L and we want the last r. I want the last one. So my range of values of r is this. Like my r can be either 2 or 3 or 4 up to 7, right? So my initial range is this. Now I'll check the middle value. That is, I'll check the bitwise AND from this L to this mid. And if it is less than or equal to k, or if it is less than k, then that means we are too far ahead and we have to move back. So I'll change my range to this one. I'll update my range to this, right? And if it is greater than equal to k, if my f of L comma mid, if it is greater than equal to k, then I'll simply do like my low equal to mid. So the answer is either this index or something above. and if f of L comma mid is less than k, then I'll do high equal to mid minus 1. Alright, so this is your entire like solution. But how do I actually check? Like, how do I find out the value of f for certain range? Like, of course I cannot iterate over this entire subarray and take the bitwise AND, because that would give TLE, like, because that would take O of n time, right? So for each query we will be taking O of n into log n time. Like, for each query we will be taking O of n log n time, because n is for the check function, like to find out the range AND for our mid, like finding out the L comma mid value, and log n is for the binary search, right? So this will not give accepted, like it will give TLE, because for each query we are doing n log n. So we have to optimize this further, that how do I make the check function? Okay, so the new problem is that how do I make check function? This is the new problem, that simply what we have to do is that in our array from a1 a2 up to an, we need to find out the bitwise AND from any index L to any index R. So that's what we need to find out. Like, we have to handle the queries of this type, right? And we have to find them efficiently, the bitwise AND from L to R in our array. So some of you who are well versed with theory might think that we can use sparse table, and that is correct. Like, you can use sparse tables here, but this problem is not intended to have sparse table, because it's just rating 1400. So that is overkill. You can do it without sparse table as well, and that's what I'll tell you here. All right. So since you want a bitwise AND, right? Since you want a bitwise AND operation, you can simply do it bitwise, right? So my point is that if you want the bitwise AND from al plus 1 up to ar, right, then you can just find the answer bit by bit. Okay, and what do I mean by that? It means that I can simply, like, for the 2 to the power 0th bit, is it 1 or 0? For the 2 to the power 1th bit, is it 1 or 0? For 2 to the power 2th bit, is it 1 or 0? And so on. Like, this is my approach, that I'll check for every bit that is it 1 or 0 in my answer. Like, in my bitwise AND, will it be 1 or 0? So how to actually check that? To check that, we can simply use the definition of bitwise AND. Like, what is AND of a range? Like, if I have so many numbers, like for a certain bit j, like for the jth bit, if I want to find out that is it 1 or 0, then when it be 1 and when will it be 0? So the bitwise AND is 1 if and only if all of the operands are 1. So 1 and 1 and 1 up to and 1. So if all of them are 1, then only it is 1, right? So that means that the jth bit in each of these numbers, al plus 1 up to ar, if the jth bit is 1, then we can definitely say that in my bitwise AND of these numbers, in my ans, the jth bit will be 1. Jth bit is 1, right? And if in any one of these numbers the jth bit is 0, then we can say that the in my answer also the jth bit will be 0. So now the problem boils down that for each bit we need to count that in a certain range how many zeros are there. Like, for each bit, count the number of zeros in range L to R. In the range L to R. This is what my problem boils down to. So if my count is 0, then so basically I have no zeros in this range, So my bitwise AND will be 1. And if my count is non-zero, like if my count of number of zeros is non-zero, that means there are at least one zero. So in my bitwise AND, my jth bit will be 0. So how do we actually do that? We can just use a prefix sum approach. Like we can store the prefixes for each bit. Like I can store that for each bit j, I can store the pref of I. The pref of I, which will count the number of zeros at the jth bit, in the prefix of um, like a0 up to a of I minus 1. So this is what my pref of I is defined, and like I'll define my pref of 0 to be equal to 0. So finally, if I want that how many number of zeros are there in the range L comma R, then I can just do prefix of R plus 1 minus prefix of L, right? So this is very similar to your prefix sum approach, like where you find the range sum. Here you are finding range AND by just doing bitwise operations, right? So that's what you can store. Pref of I will store the number of zeros at the jth bit. So like for each bit you will do this. So the number of zeros in the prefix of a0 up to ai minus 1. And when you want to calculate the bitwise AND for a certain range, you can simply use this prefix, and bit by bit you can check that for that bit is the number of zeros equal to 0 or not equal to 0. So if it is equal to 0, then your bit will be 1 in your answer, and if it is not equal to 0, then that bit will be 0 in your answer, right? So this is your entire solution. Like that's how you make the check function, right? And the binary search approach is also clear. So finally, for each query you can just do a binary search, and for the check function you can just do it bitwise, and it will give you the bitwise AND of this range, like the range AND very fast, right? So that is the solution here. And let's look at the code now. So in the code I have the test cases. Also I have the fast IO and the test cases I have, and while t minus minus I am calling solve function. So in the solve function what I have is int n c in n, int I equal to 0 I less than I plus plus c in a of I. Where is a of I? Like this a is a global array which I have defined right here. So the global array. Now for int j equal to 0, j less than 30, j plus plus. So I am iterating over all the bits. Okay, like I am in this for loop, I am pre-computing my prefix sum array. Okay, so I have defined like the prefix sum of j comma 0 as 0, and now for int I equal to 0, I less than I plus plus. If the jth bit of ai is 1, okay, then my prefix of I plus 1 is just equal to prefix of I, because in my prefix I am counting the number of zeros, right? So if it is 1, then the prefix will remain same, and if it is 0, then my prefix of j comma I plus 1 will become prefix of j comma I plus 1, right? So that's what I have pre-computed for every bit. And now I'll handle the queries int q c in q, while q minus minus I have int l comma k, c in l comma k, and I'll do l minus minus because I have used 0 indexing, but in the input they have 1 indexing. Now if a of l is less than k, like like I want to find out the maximum r such that the bitwise AND is greater than equal to k, right? But if itself, like for even r equal to l, if this number is already less than k, then definitely these are also less than k. So basically I have the condition of 0 0 0 0 0. So there is no first one, or I mean there is no 1 here, so we'll print minus 1. Now otherwise I'll have the binary search limits as low equal to L and high equal to n minus 1. Like for my R index, these are the limits. R can be L or n minus 1, like up to n minus 1. While low is less than high, I'll check for mid. Mid is equal to low plus I plus 1 by 2. Now if the range and from L comma mid is greater than equal to k, then my low equal to mid. So if my range and is at least k, then either my mid is the answer or my answer is even farther than mid, right? And if my range and is too small, like if it is less than k, then I have to go back. So my high equal to mid minus 1, right? And how does range and function work? Let's go to that. So this range and function just goes bit by bit. So for int I equal to 0, I less than 30, I plus plus. So we want the range from L to R, right? The and from L to R. So if my prefix sum of I comma R plus 1, so for the ith bit R plus 1 minus for the ith bit L. So if my pre of R plus 1 minus pre of L is equal to 0, that means that in the range of L comma R, there are no zeros. The number of zeros is 0. So my answer will have that bit as 1. So I'll add 2 to the power I into my answer and I'll return the answer, right? So that's the entire solution here. And the TC of the solution is simply, like for the pre-computation, you will take O of n into log a. So this is O of n and this is log a, where log a means the number of bits. So here it is 30. And while in the queries, so you have q queries, so O of q there, and per query you are doing binary search, so that is O of log n. And for in a check function you are taking O of log a time, log a because like the number of bits. So to find the range and you are doing number of bits operations, so O of log a. So in total your TC would turn out to be q log n log a and plus the pre-computation part. So your finally your test, like finally your TC turns out to be O of n log a for pre-computation plus q log n log n log a, right? And the space complexity is simply O of n log a because you are storing the prefix sums. So this prefix sum will take n into log a space, like log a because every bit, and the prefix sum is of length n. So this is your SC and TC, right? So I hope you understood this solution and thanks for watching.